Okay, so I have a short little lesson for today, and I'm just going to finish up section 5.8 by talking about what happens if we have molecules that have more than one central atom. All I've talked about before up to now is just where we have, just one central atom, but there are molecules where we have more than one. I'll give you a couple examples. For example, one example is ethanol, which the formula for ethanol is C2H6O, but sometimes to show how these things are put together, they're written in a slightly different way. So CH3, CH2OH. So this helps to kind of give you a sense of the connecting pattern of the molecule. So let's talk about drawing. We have to draw the Lewis structure first, and then we'll look at the shape. So this connecting pattern is sort of giving you a hint here. So what we have a carbon with 3 hydrogens attached. That's connected to the next carbon, so that's what the CH3 means, a carbon with 3 hydrogens. Then we are attaching to the next carbon. And obviously one of the hydrogens cannot be between the 2 carbons because hydrogen has to be terminal. It can only make 1 bond. If we put it between here, it'd be making 2 bonds, and hydrogen can't do that. So then we've got 2 hydrogens here, and then OH. So let's take a look at how many valence electrons we should have. The 2 carbons together each has 4, that'd be 8, plus 6 from the hydrogens, plus 6 from the oxygen. So that's going to be, is that 20? Yeah, 20. So now let's look at how many we've used in the bonds. 2, 4, 6, 8, 10, 12, 14, 16. So minus 16. I've only got 4 electrons left to add, and only one atom on the whole molecule doesn't have its full shell, and that's oxygen. And there's my total of 20. Now let's look at the shapes. So unlike when you only have one central atom, you can talk about just the shape of the molecule and give it a term like trigonal planar, trigonal pyramidal, tetrahedral, bent, whatever. When you have molecules with more than one central atom, so we actually have 3 central atoms here, carbon 1, carbon 2, and the oxygen. What we have to do is we can't just ascribe one word to describe the whole geometry. We can describe the geometry around each individual central atom, and those together are going to describe the shape overall. So we look at carbon 1, the shape around it, we have 4 bonds, which makes it tetrahedral. Carbon 2 also has 4 bonds around it, and that's also going to be tetrahedral. Finally, oxygen has 4 electron groups, so its electron geometry is tetrahedral, but its shape, with the 2 lone pairs, is bent. So this altogether is the best we can do to verbally describe it, but these shapes are going to come together to make a picture of what the molecule will look like. So I'm going to draw carbon 1 with the geometry here, and then this just goes to carbon 2. Now I'm having to take a few liberties with how I'm drawing it because just to get everything to work out right, but you'll notice that though I am sort of flipping these shapes around and upside down, I'm keeping the same basic shape. So this carbon is tetrahedral, this carbon is tetrahedral, and then the oxygen is going to be bent like that. Or it could have gone up this way. It doesn't really matter. So this describes the shape. Let's do another one. Okay, so let's do acetic acid. See, this is going to look kind of similar. CH3COOH. So this kind of implies what we want here, which is carbon with 3 hydrogens on it, then a carbon with an oxygen, another oxygen, both oxygens together. You never get oxygen-oxygen like that. And I should clarify, I will always give you the connecting pattern. You're not going to have to guess at this. And then a hydrogen coming off of one of the oxygens, right? So let's count up our total number of valence electrons. We have 2 carbons for 8. We have 4 hydrogens for 4. And then 2 oxygens at 8 each for 16. So that looks like 28 to me. 2, 4, 6, 8, 10, 12, 14 has already been used, which leaves 14 left. I feel like I miscounted somewhere. I feel like somewhere I miscounted. 8, 4. I doubled oxygen. I wasn't thinking right with oxygen. That's what happened. Carbon, each oxygen only has 6, so that's 12. There we go. That's better. So it's 24 minus the 14 used on the molecule is 10. Much better. So I'm going to fill out the octets of this oxygen first because it's on the outside. So 2, 4, 6, 8, 10. That's all I got. Now, if you look, this carbon doesn't have an octet, so it needs to make a double bond. Well, remember, it would be a perfectly valid Lewis structure to make a double bond, and it wouldn't change the shape either. That's what's really critical, is that if you have a valid Lewis structure, it shouldn't change the shape. With either oxygen, a little bit better is to do this one so that both oxygens can make 2 bonds, but if you made a double bond with the other oxygen, it would not be wrong. So now we look at carbon 1, carbon 2, and the oxygen. Carbon 1 has a tetrahedral. I'm just going to write tetrahedral because I'm running out of space, for having these 4 bonds. Carbon 2 has 1, 2, 3 electron groups and no lone pairs, so it's trigonal, planar, and then oxygen has 1, 2, 3, 4 electron groups, and it is bent because of the 2 lone pairs. So overall, it's going to look like this. Kind of similar to the ethanol structure I drew a little bit ago. COOH, just like that. Okay. So just trying to keep it short, that is how you deal with shapes of molecules with more than one central atom. You can identify the geometry around each central atom separately. So there's not one word that describes everything.